this tutorial, we will go through a material science workflow to screen a set of related molecules for properties relevant to optoelectronics, such as in OLED devices. These properties include oxidation and reduction potentials, hole and electron reorganization energies, singlet-triplet excitation energies, and electronic absorption spectra. Now, the first thing we will want to do after launching Maestro Material Science is to create a new project. So let's go to File, New Project. And we'll just call this project Optoelectronics. The charge transport material we will be simulating will be based on 2-phenylpyridine. So we'll use the Builder toolbar to first build 2 phenyl rings, followed by the nitrogen substitution. We can then create a project entry from the workspace and call it PPY, and should see now that it appears in the entry list. The next step is to generate a set of modified 2-phenylpyridines in which the selected atoms on it have been transmuted to another element. We can do this by going to Tools and then Elemental Enumeration. Now in this example, we'll type N for nitrogen for the atoms to transmute into. Then we'll pick, say, 5 atoms on the template to mutate to nitrogen, and then we'll set the maximum transmutations per structure to, say, 5, noting that in this example it will generate 31 additional structures. And then we'll click Transmute. Once the job's completed, we'll notice that the transmuted structures appear in the entry list. We can examine the variations that were made by including them in the workspace, or by including a bunch of them and clicking the Tile button. Notice the variations in positions for the nitrogens. Okay, so the next step is to actually build the homoleptic complexes for these structures. So we'll go to Tools, and then Build Homoleptic Complexes. Now this panel is used to build a set of organometallic complexes from the selected ligands, where each complex is composed of a metal and enough copies of a single ligand to fill the coordination sites for the chosen complex geometry. In this example, we'll use the select entries as our ligand, and we'll use iridium as our metal, so we'll type IR. We'll change the ligand type to bidentate. Now the coordinating or ligating atoms corresponds to the atom number. So this carbon corresponds to atom 10. So we'll change this to 10 with the lone hydrogen atom to be removed. Now the second coordinating atom is the nitrogen, which corresponds to atom 12. So we'll change this to 12. And keep everything with default settings, and then click Build Complexes. Okay, so now we can see the final set of organometallic complexes we'll be using to simulate a good charge transport material. We can again include them in the workspace, and we can use the Tile button to view several at once. We'll now go to the Optoelectronics panel, which is under the Tasks menu, and choose Perform Calculation. Again, we'll use the selected entries. We'll keep the mode to screening and note the various properties we'll be calculating. We'll change the job name to, say, Optoelectronics_PPY, and set up the job settings. In this example, I'll use 4 CPUs, but for a job like this, we recommend submitting to a large cluster with many processors, as these calculations produce quality numbers and computing time can be quite lengthy. Nonetheless, when you're ready, click Save and Run. After the job has completed, we'll go to Tasks, and then Optoelectronics, and View Results. In this example, the results have been incorporated into the project table and entry list, so we'll just click Load Data. This will load the structures and their calculated properties. Now at the bottom of the panel, we can plot these key properties. For the x-axis, we'll choose dipole. This is because low dipole moments in charge transport materials are desirable because they tend to lead to less charge trapping. For the y-axis, we'll choose hole reorganization energy. And this is because low hole reorganization energy can lead to greater charge mobility due to smaller hopping barriers. Now for the color, we'll choose oxidation potential. Now it's desirable to have a range of oxidation potentials to choose from. And this is partly because the oxidation potential of a material should be well matched with materials in the same and adjacent layers. Okay, so we can note there is a small cluster of 4 points in the bottom left corner of the plot. These are molecules with small dipole moments and low hole reorganization energies, which means that they are potentially good hole transport materials. So let's focus on these 4 structures by dragging the blue and red dotted lines. And then in the above table, we click on Show Rows Selected Only to show the plot with just those 4 structures. Now we can click Include in Workspace to visualize these structures. And we can also sort the structures based on Lmax, corresponding to the wavelength in the visible region for which the spectrum has the highest intensity. And then we can go ahead and plot the absorption spectra. More importantly, if we click on the plot for another structure, we observe that the 2 spectra are now compared in the absorption spectrum panel. This is useful as it is desirable that charge transport materials not absorb in regions of the spectrum where the pixel is emitting light. Because photons of light can go through a number of internal reflections before exiting the device, even a small amount of absorption in the wrong region of the spectrum can lead to a dramatic decrease in the light outcoupling efficiency of the device. So, being able to compare predicted spectra, as shown here, allows for the rational design of materials with less absorption in the emission window.